Hi everyone, Dr. P here, and in this lecture I'll talk about mass spectrometry. So mass spectrometry is used primarily to determine the molar mass and formula of a compound. Now notice that this is spectrometry and not spectroscopy. There's no absorption of light involved, so it's different than UV vis or IR or NMR. The way that it works is we'll go ahead and vaporize and ionize a sample, and then those ions are separated, detected, and we get a graph, the mass spectrum. Now, can you think of some ways to get an organic molecule to ionize? Well, I can think of a few. You could zap it with a stream of electrons. You could zap it with a laser. Uh, the method that is often used is what's called EI, or electron impact. So again, a stream of electrons. I'm going to show a little schematic of what a mass spectrometer looks like. Not an actual picture, but just kind of a little cartoon diagram in just a few minutes. So we get this beam of high energy electrons, 1600 kcals, or if you're a physicist, 70 electron volts. The electron volt is another measure, another unit of energy, which as chemists we don't really concern ourselves too much about. But the key here is that our stream of high energy electrons will actually knock electrons out of the molecules that get hit by the electron beam. So let's say we have some kind of hydrocarbon here, we zap it with our beam of electrons, we can knock an electron out. And we're left with now just this single dot right here. Before we had a bond, which is 2 electrons. Now we just have 1 electron in that bond. So kind of a fragile thing. And this is what's called a radical cation. Okay, we lose an electron, we lost a negative charge, so our resulting species has a positive charge. Now, what does this radical cation look like compared to the original molecule? Well, all we've lost is an electron. And remember, an electron has a mass about 1/2000th the mass of a proton or a neutron. So really it's insignificant when it comes to the mass of atoms and molecules. So our radical cation will have the same mass as the original molecule. And we refer to that as the molecular ion, or M plus ion. Okay, so M here referring to the molar mass of the original compound, plus referring to the charge on the ion. Now often the molecular ion undergoes some type of fragmentation. Why would that be? Well, just take a look at it. I now have my two halves of this molecule held together not by 2 electrons, a pair of electrons in a covalent bond. We don't have that. Instead, we have a single electron that's just ready to fall apart. So often we will get these things fragmenting, and then we can actually detect the fragments, which is kind of neat. Here's an example. So here we've got the radical cation, that single electron going on to 1 carbon, giving us a carbon radical and a carbocation. Now, these ions are sent through, and all these fragments are sent through a magnetic field, and they get deflected. The ions get deflected by a magnetic field. So smaller mass ions and higher charge fragments, so if you had a 2 plus charge or a 3 plus charge, those would get deflected more by the magnetic field. And that's because we have a fixed magnetic field, and so it's going to act a certain amount on a plus charge with a certain force, and so a lighter molecule will be moved more by that force than a heavier molecule would. Or if we have multiple charges, say a 2 plus or even 3 plus ion, that would be moved more. There would be 2 times or 3 times the force. And of course, neutral fragments are not detected. Why is that? Well, no force is exerted on them by the magnetic field because they're not charged. So typically we only get plus ions and neutral fragments as well. So we usually don't get the 2 plus and the 3 plus ions. This diagram shows a general setup for a mass spectrometer. And this is actually would be all contained in like a big sort of thing on a bench top or something. You would inject your sample molecules somehow. Those get heated and vaporized and then hit by the electron beam. And now they're going to be ionized, and then with some magnets they're sped up and then sent through another magnetic field where the ions will be deflected, and then they go to some kind of analyzer, some kind of detector. And basically the lighter fragments will be deflected more than the heavier fragments, and your detector will detect where they are. And then you have a computer, of course, as always, to visualize the results. So let's take a look at what a mass spectrum actually looks like. So there are several parts to a mass spectrum. The base peak is the tallest peak of the spectrum. Now for methane, which is this example here, the base peak is the M plus peak. But sometimes the M plus peak is not even observed. Think about that for a minute. So our base peak is our highest peak. We give that a value of 100 on our relative abundance, our Y scale. Our X scale is M divided by Z, so that's a charge to mass ratio, or sorry, mass to charge ratio. Is M over Z. So if our charge is constant, if it's +1, then our value on the x-axis is simply the mass. All right. So if we had, let's say, well, just to go back a couple here, if we had something that fell apart readily, we might not even see the M plus peak. We may never get the molecular ion even detected. But for methane, we do. And we can see that right here. There's our M plus peak. Now, if we have peaks with a mass of less than M plus, those are from fragmentation. So our molecular ion has a mass of 16, or a mass to charge ratio of 16, I should say. But this could fall apart. Obviously, we lost an electron already to make the molecular ion. So now this CH bond isn't really a full bond, it just has one electron. So we could lose a hydrogen atom and get a methyl cation here. And this has a charge to mass to charge, ratio of 15. So it would be a mass of 15. And that's this peak right here, which is actually a pretty significant peak. If we lost another hydrogen, we could get down to 14 or 13. If we lost all the hydrogens, we just had carbon with a positive charge, that would be right there, 12. Now, there's also a peak at M plus 1, which is right there at 17. We'll talk about that in just a little bit. All right. I want to take just a minute to sort of talk about, or just mention a few of the areas that mass spectrometry is used in. It's actually a pretty sensitive analytical method. You don't need a lot of sample. Unlike, for example, NMR is not as sensitive as it could, as one would like. It's a great way of identifying organic compounds, and even in identifying biomolecules. It's used in the pharmaceutical industry, in biotech, for amino acid sequencing, and actually analyzing proteins, larger macromolecules. It can be used in clinical and environmental sensing, and even forensics, detecting explosives. If you ever watch, like NCIS, they talk about, in the lab, running something through the mass spec. And that's sort of what you would do. All right, so there are quite a variety of uses, and one of them is just the simple identification of organic compounds. So let's revisit then a spectrum. And here we have benzene. And in the mass spectrum for benzene, the M plus peak is the base peak. And that's because the benzene is pretty stable. We knock one electron out, it's still gonna be there. I could go ahead and draw that for you guys here. So we could have our boom, boom, H, 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 H. And, so maybe we've got a single electron there. So now we've got like a bond and a half there. Or maybe it's between the hydrogen and the benzene. So, instead we had, maybe we've got something like that, where our benzene ring really isn't going to fall apart as readily. I mean, we still get some. We'll always get these little fragments. But the really big thing is here, what's the mass number there? Well, that's 80, 79, 78. And that is the molar mass of benzene if all you have is carbon-12. This is 78. So carbon-12 and then protons. All right. Other compounds, like for example, pentane, we won't have the M plus peak being the base peak. And we can see that here. Here's our M plus peak. So the M plus peak is going to be the highest, not the absolute highest, because usually that's like the M plus 1 or M plus 2. But our highest peak there, that's our M plus peak, but it's not the base peak. That's the most stable fragment. So we can see that with pentane, it can fragment to a bunch of different pieces, and we'll take a look at those a little bit later. The first thing that you want to do when you look at a mass spec is figure out where your M plus peak is. It may be big, like for benzene. It may be small, like for pentane. So you do have to watch out. Okay. You can also get the molar mass of the compound from that peak. So we can look here and we can see that 172. So that is 72 is our molar mass of pentane. Pentane is C5H12. Yep, that's 72 if all of our carbons are carbon-12. All right. If you have an odd mass for your M plus peak, it may mean you have a nitrogen or an odd number of nitrogens because you'll be bringing along another hydrogen. Remember, nitrogen counted as half a carbon for determining degrees of unsaturation? Again, because it's trivalent, we get that extra hydrogen. If you have an even M plus peak, it could be that you have no nitrogen atoms or an even number of nitrogen atoms. Now, there are other elements that actually have odd mass numbers. And so that could be a different explanation for an odd M plus peak. We'll actually look at that in just a minute here. All right, so let's take a look at the M plus 1 peak. Now, I've been assuming that everything is carbon-12, and for the most part it is. Carbon-13 has a natural abundance of about 1%. So, if your methane has a carbon-12 and 4 hydrogens, it'll have a mass of 16. But 1 out of every 100, approximately, methane molecules will have a carbon-13 instead of a carbon-12. So 13 plus 4 gives you 17. That's the M plus 1 peak. And it's about 1% the size of the M plus peak. Now, if you have a lot of carbon atoms, so let's say you have decanes, so that's 10 carbons. Your chances of having at least one, or having one carbon-13 atom are greatly increased. So basically it's 10 times the effect. You could actually do the calculation and do, 0.99 times, or 0.99, which would be 99% carbon-12, 0.99 to the, let me write it out here for you. Hold on here. So 0.99 to the 10th, and that equals approximately 0.90, which equals 90%. It's a little bit more than 0.90. But 90% of molecules of decane, so for every 100 molecules of decane, 90 of them are exclusively carbon-12. The other 10 have one carbon-13 in them. So we should see the M plus peak being about 10 times bigger than the M plus 1 peak. And that's basically about what we see. That's at about 10, and that's at 100. So we could estimate the number of carbons in the molecule based on the relative size of the M plus 1 peak compared to the M plus peak. Now, we can do that for some other elements as well, and I'll get to those. But one thing that we're not going to do it for is deuterium, because the natural abundance of deuterium is so small, 0.015%. Even if we had 25 hydrogens in our molecule, we would still only get, we'd still have less than 1% would be a deuterium. So yeah, it's not, it's just because it's not that common, we don't have to worry about it. But there are other elements that have more common isotopes, and we can use those to help identify what we might see. And that's where we get into the M plus 2 peak. So as an example here, we've got chlorine 35 and chlorine 37. So those are the two naturally occurring isotopes of chlorine. And we have about 3/4 of naturally occurring chlorine is chlorine 35, and 1/4 is chlorine 37. Remember, if you look at the periodic table, you'll see that the atomic mass for chlorine is 35.45. Well, that doesn't mean that every atom of chlorine has a mass of 35.45. It means on average that's the mass. 76% of the time it has a mass of 35. The other 24% of the time the chlorine has a mass of 37. That's about a 3-to-1 ratio. So you would see then an M plus peak about 3 times bigger than an M plus 2 peak, because we have a gap of 2 from 35 to 37. And so we can see that here. So here we've got, let's see, it was 110, that looks like 111, 112, 112, 13, and 114. Okay, and that 3-to-1 ratio here indicates you have a chlorine. So you're probably watching this mass spec lecture, not just because I told you to, but because you might have a halide in a halogen in your unknown. And I've told you that it'll be obvious what halogen you have by looking at the mass spec. Well, you can tell if you have chlorine by looking at the mass spectrum of your unknown. So this here is chlorobenzene. We can see we've got our peak for just benzene here at 70. That's at 78, actually 77. So there's 70, 80, 79, 78, 77, because that's if we lose the chlorine. And you can actually do things like subtract the mass of chlorine. So let's do 112 minus 35. And let me just do that here. 112 minus 35. I'm not really feeling very mathy right now. That's a 7. And 77. What do you know? And that's our peak there, is at 77. 77. So if we lose a chlorine due to fragmentation, That's what we get. All right, so the 3 to 1 M plus to M plus 2 peak ratio, that's chlorine. Bromine, excuse me, bromine consists of bromine 79 and bromine 81 in approximately equal amounts. So if you have an M plus peak and an M plus 2 peak that are approximately equal, that means you have a bromine. Okay, so if you know you have a halogen and you see this at your M plus and M plus 2 peak, you know that's bromine. That is different than if you've got chlorine. Okay, 3 to 1 versus 1 to 1. Now, what about iodine? If you had iodine, you would see a peak. You should see a peak at 127 from the actual iodine itself when it fragments. Okay, so I'll just mention that. Maybe I'll just mention it as an aside here. I'll say I can give peak at 127, or you'll get a gap of 127 between the molecular ion peak and the first fragment. So, you can see here we've got a gap of 79. Here we had a gap of 35. You could have a gap of 127, or just a peak at 127 from an iodine as it falls off. All right. So, if you don't get anything else from the mass spec lecture, just remember that about the halogens, and it allows you to identify what halogen you have very easily. Now, the other thing it's useful for is fragmentation. So sometimes students have alkanes as their unknowns, and those can be a little tricky to deal with. If you had a mass spec, then you could actually use a fragmentation pattern to kind of piece things back together. So take a look at pentane, for example. We make the molecular ion here, and then we could get fragments. We could lose a methyl radical and have this butyl ion, which would have a mass equal to the M mass minus the mass of the methyl radical, so minus 15. So we'd have an M minus 15 fragment. If we got this bond breaking here, we'd get a propyl ion and an ethyl radical. And so the mass of ethyl is 29. There's 2 carbons, 5 hydrogens. So our propyl radical is an M minus 29 fragment. And then we could also get, a propyl ion is an M minus 29 fragment. We could get a propyl radical and an ethyl ion, or a butyl radical and a methyl cation. But again, only these guys here in green, the charged cations, are detected because mass spec only detects the charged fragments. All right, what does this look like then? Well, it looks like the following. We have our little tiny M plus peak here, but then we have peaks at M minus 15, M minus 29, M minus 43, M minus 57. We have one at M minus 41. That's kind of interesting. That might be due to something else, which I'll talk about in just a little bit. But, if you see these types of patterns, you can think, oh, I've lost a methyl here. Oh, I've lost an ethyl here. You can also work backwards and say that, oh, that's at 15. So that must be a methyl cation. That one's at 29. That must be an ethyl cation. This is at 43. That must be a propyl cation. This is at 57. So that would be a butyl cation. And 72, of course, is my pentane molecular ion. All right. In general, the relative amounts of the different fragments you get depends on their stability. So it definitely looks like the N-29, so our propyl radical is the most stable. And actually propyl ion is the most stable. And the bigger ions and the smaller ions are less stable. So it's more likely to split into 3 and 2 than it is into 4 and 1, or stay intact. All right. So here's another example of a fragmentation. And here we have 1, 2, 3, 4, 5, 6, 7. So we have an isomer of heptane, and here's the molecular ion. When it fragments, it's very likely to fragment in the following way, where we get a tertiary carbocation. That's nice and stable. And then we get this primary radical that's not detected. So we've lost 3 carbons here, and 2, 4, 7 hydrogens. So that's going to be 43. So this is our M-43 peak here. And it's tertiary. So this is probably going to be your base peak, your biggest peak, because that is so stable. And you can actually use the fragments you observe to kind of piece things back together like a puzzle. If you can piece your fragments together, you can maybe figure out what you had. Now, the last thing that can happen, which can explain some other peaks that you may see, are sometimes, or the other thing that can happen is that sometimes you can get different types of fragmentation if you've got different types of functional groups. So like an alcohol can undergo an alpha cleavage, where we cleave this bond here, and we get this kind of this compound, this ion here, this resonance stabilized ion. Or we could get a dehydration and lose water and get a molecular ion, in this case M-18, because the molar mass of water is 18. So if you see a gap of 18, it could be from losing water, if you know you have an oxygen in there. Carbonyls will undergo a rearrangement to give a more stable ion. In this case, this is an enol ion, and then also an alkene, which is not detected, but this guy would be detected. We call this a McLafferty rearrangement. There are a variety of other rearrangements that can occur as well, but they're kind of, beyond the scope of this course. But really, just for, the take-home message is we're going to use mass spec to get molar mass identity of halogens, number carbons, question mark, presence of nitrogen, question mark. And then the other thing is our fragmentation patterns. Oops, ERN, no, not an M, an N. There we go, fragmentation patterns. All right, so, and these are kind of in the order that, I think maybe presence of nitrogen is, they'd use that a little more frequently than number of carbons. But really, molar mass from the molecular ion peak, and then identity of halogens. That's going to be the big one. Remember, chlorine is 3-to-1, and bromine is 1-to-1, and iodine would be either a peak at 127 or a gap of 127 from your molecular ion peak to the next fragment peak. All right, so hopefully that's enough to get everyone started. And, if you didn't need to analyze a mass spec for your unknown because you didn't have a halogen, great. Now you know some about mass spec and you can apply that on the ACS exam. All right, well, until next time.